So we're talking about making a box now bounce around the screen, right? In 2 dimensions, picking a random starting direction, just kind of shooting off and bouncing around all the walls that might be there. This is 2 dimensions, right? So we're up in the game from 1 to 2 because we had our box, or we had a circle, right? That was going straight up and straight down. That was messing with the Y, right? But now we want to mess with the X as well. So we talked about that before. Let's figure out how to do it. All right. So we want to like recreate this Office episode where you get the little DVD logo bouncing around the screen. Okay, that is our goal, and we kind of talked about it a little bit, right? So we want a box. We want to give it a random direction, maybe that way, and then every time it hits a wall, it needs to bounce off in the correct way, and hopefully, maybe once, eventually, it will hit a corner. Something like that. So, we have talked about most of this already. I'm just going to remind you of what we went over, because it's just going to be mostly coding up what we decided last time, okay? So our goal to start, as usual, is we're going to draw the bounds in which the ball is going to bounce, or the box is going to bounce, and we'll just keep what we've been having. So that'll be like the 400 by 400 bounding square. So it's centered at 0, 0, and it is a 400 by 400 square. Boop. Let's see if I can draw perfect. This is not a square, but it's close enough. And so if it is a perfect square, that means if 0, 0 is right here, that means right here is negative 200, positive 200, yeah? And then over here then is also stuff involving 200. It's positive 200, negative 200, yeah? So there's those. And, all right, we'll do that. Got the square drawn. Then we want to make a square, make a tinier square, right, inside of those boundaries at some random spots. Like pick a random spot. Could be anywhere, here, 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 wherever you want it. Should have all of those as a possibility, but maybe it chooses this place. All right, so we'll make a random square there. The turtle will be that tiny square, okay, just like he was the ball. And then we'll give him a random direction. All right, we'll give him a random direction. You could choose any direction, that way, that way, that way, that way. Let's say we randomly choose this one. And remember how to represent direction. This is what we need, right? So we had we were representing up and down motion by an offset in terms of the Y, but for a sideways motion, we can also include an offset for the X, right? So this direction, that kind of arrow, it means move a little bit to the right, so positive X offset, and move a little bit up, so also a positive Y offset. Is that coming back to us? So just shout out if you have any questions about that. But that's going to be what we start out the box doing, right? Give it a direction and let it get ready to move that way. And then just to move it, just like take its position and modify it by this X amount and this Y amount, and then suddenly it will be over here. Yeah, that's what will happen. So it's going to look very nice and satisfying once we get it working. And then it's just a loop, right? For until the end of time. Now it's like draw a new frame, just like we were doing for the bouncing ball. It's going to be take our box. It's got a direction. Move it in that direction. Shove it that way because you got an X offset and a Y offset. Use them to nudge the box's position, right? Because this is like velocity. Use it to change the position, and then the box will just like keep going that way, that way, that way, as long as there's not a wall, right? Once we hit a wall, we'll notice it with like an if statement because like our Y for the top wall got a little too big, something involving 200, right? And then we want to change our direction. We were coming in this way. We want to bounce off that way. Yeah, the nice, perfect way of doing that. And then we'll have a new direction, something involving the old direction. It'll look a lot like that, but like some of those things are going to get swapped, negated. And then we'll just keep on doing that, right? Move in our current direction if there's nothing in the way. But if we hit a wall bounce, that's pretty much the game. We'll just have to put in the details, right? So yeah, that's most of it. And then you hit another wall, you bounce off some more in the correct direction, right? So you change your direction. You're coming in this way, change your direction to be coming out that way. Yeah. Any questions about that? Remember that? So that's where we're going. And all right, so here was what we decided was how we were going to do that. So let's see here. We want the turtle to be our box, so we'll do that. Turtle can become the box. That's fine. That's in the turtle library. we look into that, Python turtle, it's turtle.shape, right? The shape can be turtle, like we were having before. It can be circle, like it was for the bouncing ball, and then we'll make them a square. Turtle.shape square, the string square. That will work. And then, all right, the direction, right? The direction is a couple of offsets together. That's what we're doing. So let's say this is my box. Boop. This is my box. I want the ability to like go in any of these directions. This one, this one, this one. And if you think about it, we learned that no matter the direction I could go in, there's always like, if it's two-dimensional, there's always like go a little bit in the x direction. Maybe don't go at all in the x direction. If it's straight up or down, that's fine. But have the potential of going, like being nudged in the x direction and also the y direction, all right? Somewhere, either up or down, left or right, all right? Some combination of those. So yeah, that's pretty much the game. And our direction is just going to be essentially two random numbers. Like maybe that's the direction that we choose. And how do we get that? What does that mean? How do we store it? It will be using a couple of offsets, right? So there's going to be this arrow. You can think of it as, well, it's a little bit to the right. So go x positive, and it's a little bit up, right? Go y positive. Maybe it's like 2, 3 or something. You can store those as numbers. Does that make sense? That's where we're going. So we'll just call this x off for x offset, and this can be y off for y offset. And yeah, that's how we'll move the turtle, by nudging its position with these offsets every frame. So yeah, we'll have our two numbers, our x offset and our y offset, to talk about where we're moving. And then every frame, as long as we're not hitting a wall at least, we're going to move the turtle relative to this direction, right? In that direction. So let's say that our turtle was right here. He was at xy. That was his current coordinate. After a frame, we want him to be moved in this direction. We can use our x offset and our y offset to move him over to here. Yeah? What will his new position be after a frame, after we do all this? Just like, well, take his old x, move him to the right by x offset, right? That's the new position of this turtle, of this box, will be x plus x off, the x offset. And then same with the y. Take the y, make it a little bit bigger, nudge it by the y offset. That will move them exactly in that diagonal way. Y plus y off. So for the y offset. All right, does that make sense? That's what we're going to do, and that's how you get that diagonal movement. So it's beautiful. It's going to work out just fine. So we'll do that. And yeah, so every direction, remember that every direction has some sort of xy offset. If you are, let me redraw this thing up here. This one that we were showing is like, all right, positive x, positive y. This one over here is negative x, go a little bit to the left, right? Negative x, positive y, still go up. This one's negative x, negative y, right? Go left and down. This one's positive x, negative y. Yeah, so go right, but go down. See it? And then everything in between, maybe like go a little bit more in the y than the x for this one. Yeah, that's how you can get every direction under the sun. And then like perfectly left and right, for example, that's 0y, and all x. And then same for up and down. That should still be randomly possible. We'll choose 0 for the x direction. Just go straight up, only y. So those are like special cases, but it'll all still work out. All right. And yeah, every frame we want to move that x coordinate and the y coordinate by that amount. All right. So that's the goal. And you know, I guess let's do that. Let's just get that started at least. So I'm gonna open up idle, and let's do as much of that as we've talked about. We'll get to the bouncing off the wall, like that still needs to happen. Let's see. So we'll do that. Let's at least get a two-dimensional random direction and moving in it. So I'm gonna open up an old file. What do I want to call this? Do I want to steal? I don't want to steal the one with gravity. What was this copy one? Did I do anything special to this copy one? I included time. Now let's just go back to the old lecture 24 bounce program. So I'm going to steal, I think it would be best for me to steal this one. And so this is just the oldest program, the first bouncing program that we wrote with just constant speed, because that's what we're going to do here. This constant speed, we're going to move a box. All right, so that's this program. So that's what I'm using from lecture 24. I'll start with that. All right. So I'll make a new file for today. I'm going to steal all this and put it here. And now the question is, where do I want to put it? Let's make a folder. So 27, lecture 27 is today. So that's where I'll make it. And what should I call this? I guess I'll call it 2D bounce. All right. So this is still just the old program. Let me close out the other one. So here's this one. It's still the old program. It's still a bouncing ball right now. I guess we can change that first if you want. We got to make the turtle not a ball anymore, but a square. So that'll be easy to fix. That's just the shape. So instead of shape circle, we can say shape square. So instead of making the turtle ball, make the turtle the square. There. Square. And the color of the turtle is whatever the fill color is. So instead of pink, maybe it can be purple today. Cool. And the stretching amount is still the same. The width is still going to be 40. It's just like, it's not a radius anymore. It's not a diameter anymore. Now it's legitimately a width. So there we go. So now we're going to have a square, at least. Still going to bounce up and down only. But see how the width is still 40. It's still perfectly grazing the wall. So all those numbers are still correct for us. That's good. And then we got up and down motion by having this offset, right? And really, this was a y offset. Yeah, we're messing with the y of the turtle. We're never changing the x right now after we start the program. So we're going to mess with the x as well now. So this is really y offset. So maybe we should change that everywhere. All right. So let's see here, because we still have the bounding square. That's still correct to do that. So the turtle's a square now. We need still like the position of our turtle. Like where should this thing be right now? We'll make it more random in just a second. But right now this is a y offset. Yeah. So let me change that everywhere. All right. So instead of turtle offset, the one that we've been using is turtle y offset, yeah? Change the y by the y offset. Mess with things, change the turtle y offset by -1. Y offset by -1. All right? I think that was everywhere. So really that was the y offset that we were messing with for that original program. That was the only thing that we were ever changing, right? It was a y offset, not an x offset. We were offsetting the y every frame. Every frame we were letting the y be messed with by the y offset. All right, so there was that. Let's see here. That's more or less the answer there. So change the turtle's y coordinate by the y offset there. Something like that. Okay. So yeah, with that, we're making progress. Now let's have an x offset. Yeah, because that's what's going to give us our two-dimensional direction. If only I had an x offset, I could mess with the x offset, or let that mess with the position. So add that in every time, just like I'm adding the y in every time right now. All right? So that's where we're going. Let's do that. So let's pick a random y offset as well as, I guess this y offset is hard-coded right now. Should we change that? Maybe we should change that. Let's make the y offset be random. So like we want to be able to like go up, down, left to right. So the y offset could be like a little bit up, a little bit more up, a little bit down, a little bit more down. Could be straight down. So let's have a random number between like 0 or -1 and 1, because it should be negative as well. So you can make a random number. So like we want the ability for this number to be like 0.5, -0.75, and these are floats. These are numbers with decimal places. They're not ints. So I can't do rand int like I was doing for other things. So I would like a random float, please. Python random. And the way to get one is it's uniform somewhere. You say random.uniform, and that will give you a random number that is a float between the two things rather than just an int like rand int does. So here, let me show that to you. you say random.rand int, like -1 to 1, then you're only ever getting a number between like -1, 0, and 1. Those are your options if it's an int, right? Those are the only whole numbers within that range. And I'm randomly not ever getting 1. There we go. Random.uniform, though, that one, that will give you a random float with decimals. Random.uniform. So give me a random number between -1 and 1 with decimals involved. All right? So that would be nice to have. Look at it. Nice and with decimal places. So if you want to be very pedantic, you can be like -1.0, +1.0, because really you could have been giving float things here as well. So there's my random number. This one's very close to 0. This one is a little bit -1. This one is pretty positive. This one's a little bit less positive. So that's going to give us our random direction, right? Just a little bit nudge, where x's and y's could be negative, could be positive. So this, I think -1 to 1 is fine. But you can play around with this because like larger numbers, you know that gives you more speed, right? So let's let it be between this range for now at least. That can be where the y offset lives. Like it can be somewhere there, all right? Somewhere between -1 and 1. And then same for the x, right? We would like a random x offset to figure out what our direction is, right? So let's have an x offset in addition to the y offset, because if I pick a random number, like maybe I pick -2 for the x, right? That means go that left that way. And if I pick +3 for the y, that means go up that way. And so that corresponds to that direction. See how that's going to work? That's what I want. So there's y offset. Let's have an x offset as well, exactly the same. Some random number between -1 and 1. That will nudge me in the x, and the y will nudge me in the y. Cool. So yeah, these two variables together will form our direction. Yeah, that's what we want. So we just need to use them now. We're already using y because that was the old thing from before. We all changed it to y. So every frame right now, like forever, draw a new frame. Every frame, we're letting the y position of the turtle be messed with by the y offset. We want to do the same thing for the x because that's how we get diagonal movement, right? Every frame, take wherever we are and change wherever we are relative to our position triangle. So like go a little bit more in the x offset and a little bit more in the y offset, or less if those were negative numbers randomly. That will get us diagonal movement, right? We're already doing y stuff. Let's also do x stuff. Okay, that's what we want. So let's let that happen. So it's really just one more line, right? We got a random x offset. Let's use it. Change it every time. Let it influence the current position of the turtle, just like we're letting the y offset do. Boop. So change the turtle's x coordinate by the x offset. So turtle x needs to change by the x offset. And for similar reasons to like, I'm messing with a global variable. It was just defined outside of this draw frame function. So I have to say global turtle x because I'm changing it. Right? Otherwise, it's going to make a separate variable. It's going to like overshadow the old one. And we don't like that. So for similar reasons, we're eventually going to change y offset. So let's do this. X, or turtle x offset. Let's just all put those there, even though I haven't changed turtle offset yet. That will be part of the balancing. Maybe I'll deal with that later. But yeah, that's where we're going. All right. So yeah, now I have a random direction because I have two variables. I picked a little bit in the x and a little bit in the y. Maybe it's like -x, -y. That will give me like that way direction, down and left. So yeah, now I've picked them and I'm letting them influence the position of the turtle every frame. All right. So change the x, nudge it by the x offset. Change the y, nudge it by the y offset. And we can print what our things are right now. Like print turtle x offset, turtle y offset, to see what they are. Like what were our random things? And let's see if we can like understand why it's moving that way when we have those particular offsets. So here, let's see what happens. Look at that. It's moving a little bit to the right. You see it ever so slightly moving to the right. And it looks like, do you see how we have a decent y, and we still have up and down bouncing just fine. We still have a decent y, that's like 0.70, but the x, you see how it was positive, it's moved to the right, a little bit to the right, 0.2, so a little bit less than the y. So it's like that way. that make sense? And of course, we're falling off the screen eventually. That's beautiful. I like that. Yes, let's try again. This time we get a random direction that is, all right, this one is negative x direction, so it's moving to the left, and then positive y, but it hit the top wall at the very start of time. So that's why it's doing that. But now it's negative x, positive y, so moving up, but moving right. See that? Does that make sense? How those two numbers will correspond to a diagonal movement. Sometimes those numbers might be 0, but randomly that's not very possible. So let's try one more time and see what happens. Because then we still need to put right now I'm putting the turtle at the very top of the screen. We don't want that. Ooh, there he goes. So this one's about even. It's about negative 0.5 and positive 0.5. So it was moving pretty much left, or was moving left and up, but it hit the wall. So like it was going to go that way, like perfectly 45 almost, 45 degrees that way. So yeah, that's what's happening. Any questions about that so far? Just like we added another variable and let that affect the x position, and suddenly now we're getting nudged diagonally. Does that make sense? That's so cool, I think. So let's see, we got that. We also need a random starting point for this turtle, right? Give him a random spot to begin his life, because right now I still just put him at the top, the tippy top. So let's give him a random position as well within our square, our bounding square. So that's this, right? The initial position of the turtle is governed by these two variables. Like, what is the first value for turtle x? What is the first value for turtle y? X was a little bit random, but the y we were hard coding to be like right at the tippy top of the screen, so of the little box that I was living in. So let's just do something similar to turtle x for turtle y. It'll be like negative. Let's make it like negative 150. It'll never go out the range if it's 150. So let's do the same for turtle y. So now it'll be anywhere, more or less, within the initial bounds of our screen. Cool. So that one happened, and so it was a little bit positive, a little bit positive. So initially it was moving that way, right? It was moving right and up. It was moving a little bit more up than it was right, because the y offset was bigger than the x offset. Yeah. But we're getting a random spot for it. Oops, I don't want to minimize. So that's so cool. Just like a few more variables, a little bit extra work, and suddenly we get nice things. So let's try to get this all visible. Ooh, that's interesting. See how this one is almost straight up and down. Almost straight up and down, because the initial direction was a tiny value for the x offset, like 0.04. So it's moving a little bit to the right, positive x still. And then the y was pretty negative. It's closer to negative 1, right? So we're getting more movement in the y every frame than in the x. You see how that's working? Maybe if you stare at it for long enough, you can kind of see it very slightly going to the right, but it's very slowly going to the right because that's a very small number. Yeah, that's why that's doing that. So, are there any questions about what we got going on so far? I think I showed you enough examples. Does it make enough sense? We got more to do. I guess, honestly, there's not too much more to do. I do want to clean this up a little bit, and then we're going to need sidewalls, because just for free, we got the top and the bottom walls with what we already had, which is beautiful, the correct kinds of bouncing. So, yeah, that's lovely. All right, the next thing I want to do is I would like to get a better random direction, because there is a bit of an issue right now. If you think about it, we kind of talked about this a little bit before. Every direction has a certain xy offset, just like this particular direction has a certain xy offset. Maybe this was like 2, this was like 3. But what if, like, pretend this was our offset. It was a perfect 45, right? There's actually a few different ways to get a perfect 45 using our random numbers, aren't there? This could be 1, 1, right? That's our direction. That's perfectly as much left as it is up, or sorry, as much right as it is up, right? That would be perfectly 45. But also, what if this was your direction? These were your random numbers. 0.25, 0.25. Do you see how that's the same direction? You could randomly pick that one and go in the same direction, but you just move slower because you're being nudged a little bit less every frame. Do you see how that's just by the way that we're picking our random directions right now, we've also kind of picked our random speed as well? I don't like that. I'd rather just have a random direction, same speed no matter which direction we picked. Does that make sense? That's what I would like. So let's make it so that no matter which direction we pick, like no matter which random numbers we pick that give us that arrow in that particular direction, let's make sure, let's like stretch or squeeze the arrow along that direction so that by the end of our process, we'll always have an arrow that's exactly length 1. Does that make sense? Like the hypotenuse is length 1, because that'll move us exactly 1 unit every frame, no matter which direction we pick. Right? Because I could have also just picked this one. Right? It could have been, what? Just to drive the point home. We could have also randomly picked 0.5, positive 0.5, right? Again, that's the same direction, but it's a different speed. It's like, it's in between these two. So let's like, no matter which of these we get randomly, let's just stretch it or squeeze it so that it's always exactly length 1, right? There's a way to do that. That's what I want, and that will give me a constant speed, okay? That is called normalization. If you've taken Calculus 3, you will learn about this there at least. But we would like to normalize our direction vector. If you've heard those words, that's what we want right now, right? So like it's a triangle, we want to make sure that its hypotenuse length is 1, right? Because right now, like this one would have been like root 2, this one's smaller than 1, that one probably also smaller than 1, I don't know. So I would like to stretch it or squeeze it so that it's always 1. All right, so I have some direction triangle. I've got A and B, and I want to make sure that C is 1 by changing A and B, because those are my offsets. All right, so I want C equals to 1. That's what I like to have to happen, and I can figure out what C is. Right, that's the Pythagorean theorem. I'm gonna be like A squared plus B squared equals C squared. Right, I got A squared plus B squared is equal to C squared. And if I just take the square root of both of these, I get rid of that. And so C is whatever this is. I would like that to be 1. What I can do to get 1 is divide A and B by the initial value of this. All right, let's have an example. So let me show that to you and why that will work. Let's say that we were 0.5, 0.5, right? Let's say that our I don't know. I'm going to make a new slide. I'll show you why this works. Let's say that we did randomly pick. Go away. We randomly picked our offset in this direction. It was 0.5, 0.5 for x, 0.5 for y. So right now, this length, C, that C is equal to the square root of 0.5 squared plus 0.5 squared. Yeah, whatever that is. And so let's do that math just quickly. Let's do math dot square root of 0.5 squared plus 0.5 squared. Import math. I guess I haven't imported math yet in our old program. So it's about that. So that's smaller than 1. It's going to move slower than a size 1 thing. So we want to stretch out that arrow. All right, so it's like 0.71. So C is about 0.71 right now. So what I'll do to make this arrow longer is I can divide both of these numbers, the x and y offsets, by the current length of that thing. Because if it's smaller, it'll make it bigger. See that? Because I'm dividing by something smaller than 1. So what I'll do is I'll make this one. I'll say, I'll turn this into 0.5 over 0.71. I'll turn this into 0.5 over 0.71, or whatever that is. So I'll take this. And that's how I will scale my initial things. And so actually what's going to happen is it's just for quirks of math. I'm going to, like the resulting thing is also 0.71, which is kind of funny. So that's just a quirk of the square root of whatever we got going on right there. So I will now transform this into this arrow. It's now going to be 0.71-ish, 0.71-ish, dot, 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 dot. And I claim, if it's positive that, the length will now be 1. All right, because that will give me a perfectly moved, I'll get a perfect 1 unit of movement every frame now. So here, because like, what's this length? That's 0.71 squared plus 0.71 squared, the square root of that, yeah? Let's see. I'll just type it in. Math dot square root 71 squared plus 7-1 squared. Look at that, for 2 decimal places at least. If you kept it all the same, it's the same. So that by doing that division, I have now made this arrow longer. Does that make sense? Now it's perfectly size 1. Perfectly length 1. It's been normalized. If this value was bigger, like if this value was bigger than 1, if doing that division would make it smaller, it would squeeze in the arrow because it was a little too big. All right? Does that make sense what we're doing? That's what we want. And so if I do that, then it will be happy. And then now, no matter the direction I pick, it's like I've picked a direction along like a unit circle, kind of radius 1. It's like no matter which direction I picked, I will always make sure the arrow in that direction is length 1. It's always length 1, no matter which place I've chosen. All right? That's what I will get now for free. Okay? Based on how I'm doing this. So, okay. Let's do that. That's called normalization. And it needs the math library because we need to take the square root. So here, yeah. So it was, whatever this was, let's change it now. All right, let's stretch it or squeeze it, however we need it. Okay? So, and I don't need to print that anymore. Keep it there just in case we want to see it later. But what we want to do is it's called normalization. Let's normalize our direction so that it has a length 1 hypotenuse, because it's a direction triangle, right? We're going to divide by the current length of the hypotenuse for the x's and y's to get, we're going to do this exact process, figure out what the current length is, divide our x offset and our y offset by that length, and then suddenly, using those new x's and y offsets, then we already are going to have a length 1 triangle hypotenuse. Right? So let's get the length of that hypotenuse right now. Let's do this calculation with our current x and y offsets. So that's going to be math.square root. So square root of x offset squared plus y offset squared. That's that squared plus that squared. All right. And then that's like our length, direction, hypotenuse length. I'll just use a very long variable name. And then I want to divide my x and y by whatever that was. Like if it was 0.71, divide it by that. Whatever's in that variable. So take the x and y offset, divide them by this. So whatever the x offset is right now, keep it as it is, but divide it equals this divided by that. And that's doing that process. Okay. Same for the y. And then now for sure, now the length of the hypotenuse is 1. Okay? Does that make sense? That's what's going to happen now. So let's see here. I think that's what I wanted. Cool. Now if I rerun it, I guess, here, let me run it without doing this again. So let's get rid of, I guess, don't change it. Let me not have these lines take effect right now. And let me kind of show you what I meant by, let's try to get some directions that are almost the same. So that one, remember that speed in your mind. That one's faster, right? Remember that speed in your mind. So randomly, if I don't do this, I'm getting some random speeds in addition to my random directions. That one was about the same. Let's see if I can get a smaller speed. So if I don't do this, I get some speeds all over the place. That seems even faster, right? So, all right. Now, when I add these lines, let them take effect. Change the x and y offsets to normalize them. Make sure the length's always 1. Now, the speed will always be the same no matter which direction I shoot off in. So remember that speed. It's always going to be that speed now. See it? Exactly the same. One more time. Beautiful. I like that. And now you can mess with the speed if you want by like multiplying the x and y offsets by something now, because like the length is 1, you multiply it by 2, now the length is 2 or something. You can do that. But now you have control. All right? That's what we like. So yeah, I think that's what I wanted to do for that normalization process. I hope you see the point of it. Are there any questions about what we've done so far? We made a lot of progress. We got a random, horizontal, and vertical offset to get a diagonal movement. We're moving diagonally correctly right now at a constant speed, no matter which random direction we just chose. So that's most of it, honestly. We just need to bounce off the walls now, right? So the last piece of the puzzle is, what do we do to bounce off the walls? So let's see here. Let's draw our bounding square. I'm gonna have some examples of this. I'll do my best to draw a bounding square. That's exactly a square. So we better think of our numbers, because the x and y's are mostly the same. Like you see that we're still bouncing off the top and bottom walls correctly. It's like those ideas still hold. But let's kind of talk about exactly what's going on. So here's our bounding square. So that's 0, 0 right in the middle. And so that means up here is negative 200, positive 200, and over here again was, well, this is positive 200, negative 200, right? And so all these, think about all the lines that are bounding this box. This line right here, this top line, that's our y equals 200 line, yeah? Y equals 200, and like this left side, like we're hitting the left side of the wall, this is x, right? X equals negative 200 right here. Right, that's the bounds of our box. It's 2, 0, 0. We know what happens when we hit the top and the bottom walls, right? We've already had this in here. It's like we hit the top wall, if this is true, right? If the y is trying to get exactly equal or even bigger than 200 minus the width over 2, because you do have to play that game, right? So if this is our, like if we're hitting the top wall, we know that that is true if we got this going on, right? Like our box is right here, and remember that our box has width 40, and the location of the turtle is always relative to his center. So if the turtle is right here, just grazing the top wall, where is the turtle? Where does he think he is? It's always relative to his center, so it's not 200, because that would put him right here, right? The y is not 200 when he's grazing the top wall. The y is 200 minus half of the width. So the width is 40, so half the width is 20. So that means this line right here, that's like the top part of wherever the turtle should go, that's y equals 180. Yeah, that makes sense. That's what we've already done that. That's pretty much what that will become. Okay? And so same is true for the left and right walls. So like if we're at the left wall, we're exactly hitting the left wall. Well, that means the turtle's here, right? This is where his center is. And so if he's 40 by 40, that means that the x coordinate that got him there is not x equals negative 200, right? Not negative 200, but it's x equals negative 180. It's negative 200 plus half the width, right? Plus that, right? To get him over there. Okay? Because if it was exactly negative 200, he'd be right here, already over the wall. So that's not. That's too late. Okay? So, yeah. Is that making that sense? Because that's going to be true for everybody. So same for the right wall. It's something involving 180, right? So if we're over here just grazing the right wall, that means the turtle's center, where he thinks he is not 200, because that one put him right here, right? His center for the x, at least, is involving 180, because that's 200 minus half the width. Yeah? And then same for the bottom wall, because we've already done that. I'll go fast. Like if he's grazing the bottom wall, that means his y is a little too small, but it's not exactly negative 200. That's y equals negative 200. It's y equals negative 180, right? For all these same reasons. Because negative 200 moved up by half of that width. Negative 180. Okay. Do those numbers make sense to us? Mostly stuff that we've done before. But yeah, now we have to remember how to bounce off walls. All right. So we know when we're at a wall now. All right. We know when we're at a wall. What do I want to do here? Yeah, I'll do that later. We know when we're at a wall. All right. Now we need to know what to do when we hit a wall. All right. So this is what we've learned. We want to negate part of our offset when we hit one of the walls, and it depends which kind. All right. So let's remember what happens here. So we learned last time that we want to, if we hit a side wall, left or right wall, it's the x offset. It needs to be flipped, the sign of. Let's remember that. All right, and we'll turn this into a function eventually. So let's say we hit the sidewall. Oh man, all right, let me use PowerPoint to make straight lines because obviously I'm not doing that well today. Thank you, PowerPoint. All right, let's say that we're right here. We're hitting this wall, we're hitting the left wall, and we're just grazing it right now. So here we are. There's our center, and we're hitting the wall. We came in this way, right? We came in this way, which means we want to bounce off that way. Yeah, we want to bounce off that way. How do we get that direction? That's like we were coming in this way, boop, just like that. We want to bounce off exactly that direction. So that's kind of this area, right? That's what we want. So if we were coming in this way, what does that mean our x and y offsets were? It's like, keep them as variables. This was whatever our x offset was, it was for sure negative, right? Because it was moving us left, yeah? And then the y offset was for sure positive because it was moving us a little bit up, right? So that's whatever it used to be. What does it become when we hit the wall? Well, you see that the triangle is the same triangle. It's just been mirrored, yes? So the y offset, we still want to move up after we bounce off, right? Still move up. So keep the exact same y offset. Do nothing to the y offset. It's the x offset that needs to change. Instead of moving left and up, we must move right and up at the same amount. See that? So the same distance here, it's just in a different direction. So it's positive versus negative now. So whatever this used to be, we know it's negative. You can like do the absolute value if you really want to, but just like to make it easy on us because it'll work the same for the sidewall, the other side. Just like take it what it was and like flip the sign. That's what it needs to be, right? It was negative, make it positive by flipping the sign. Does that make sense? That will fix it. That will move us off in the other direction, and we do the same thing for the other wall. For the other side wall, it's still the x offset that needs to be negated. So like if we hit this wall, we hit the wall because we were coming in that way maybe. We want to bounce off then this way, and what does that involve? Well, we were moving right and up. We would like to now move left and up. See how keep moving up. Don't change the y offset. Negate the x offset. So either side wall, it's the x offset that's being flipped. Yeah? Questions about that? Does that make enough sense? And you can now imagine the top and the bottom wall are going to do the same thing, but it's going to be involving the y offset, right? We've already actually done that. That's what we did before. We just didn't call it the y offset when we had the bouncing ball, right? But it's working. It's working, and that's what you need. So let me just show that to you quickly. So like if we hit the bottom wall, how did we hit the bottom wall? It's because we were moving down a little bit, right? Our y offset had some negative direction to it. So let's say that this was our arrow, so it was negative y and positive x. So it's moving to the right a little bit and down. We want to bounce off this way, right? Which involves keep moving to the right. Don't change the x this time, but move up instead of the down. See that? So it's flip the direction. We're going down, go up with the same amount now. So flip the y offset. Okay? That's pretty much it. All right? So negate the x offset if you hit the sidewall. Negate the y offset. That's the part of the direction you want to change if you hit the top or the bottom wall. Okay? That's what we'll do. All right? And so this is going to get a little complicated because we're going to add a bunch of more if statements. So let's package this into a different function, let's say. Let's make a bounce if hit wall function. Okay? And that will deal with the bouncing. So watch how this makes this easy. So let me steal, oops, no, let me steal all this. Boop. Or actually, not the comment. Let's take this, and then I'll call this bounce if hit wall. Do you see how draw frame becomes very simple? It's like, all right, change the thing, bounce if we need to. All the logic will be packaged into this function that we're about to make. That'll be very nice. Makes it easier to reason about this function. Now it's a little bit smaller. All right, so I'll take everything I need to do about bouncing and put it into this function, including all the old stuff. So this is the top and the bottom wall, right? So we have those, and you see that these are messing with the y and the y offset, and they're eventually going to mess with the x and the x offset. So I'm just going to steal all these global declarations here because I want to mess with global variables. You have to say that if you want to do that. And so, all right, this is the top and the bottom wall, or I guess this is bottom and this is top wall, right there. Now let's do left and right. All right, so I'll just add some more ifs, just to make it easy on ourselves. So let's see here. I can honestly mostly copy and paste these if you think about it. So it's very, very similar. It's like, all right, now let's let these two be sidewalls, right? So these two are top and bottom. I've copied and pasted them to be, these will be talking about the sidewalls. And, all right, which wall now? So it's going to be involving x's, right? So if we hit a sidewall, something is true about the x coordinates, like less than or equal to negative 180, greater than or equal to positive 180. So, or negative 200 plus the width over 2 on the x, right? So this is negative 180, right? If the x is trying to get so small, it's way over here. That's the left wall, right? So this is, we either hit the left wall, or we're trying to go, I don't know, to the left of it, or outside of it, however you want to say that. We're trying to go, let's say, past it. Boop, something like that. So move the turtle back inside in the x, right? So we're dealing with x's now. And then change the turtle, oh shoot, this is supposed to be y offset, y offset. Now it's going to be x offset a bunch of times, right? Change the turtle x offset so that we move, not upwards, but we're moving left. Now we want to move to the right now. Because the only way we hit the left wall is if we were moving to the left, right? So, yeah, bounce off by negating the x offset. Just like that. So I got to change x to everywhere. But that will be bouncing off the left wall. So something involving the x coordinate, right? Mess with it, rein it back in if it's a little bit less, move it back inside, and then change the x offset just like we were talking about here. That's doing exactly this. So that the next frame, we're bouncing off a different way. Different now to the right instead of the left, but still up or down depending on whatever the y offset used to be. Don't change the y. Okay? And then same for the right wall. So you hit the right wall if the x is trying to get a little bit bigger than 180, right? 200 minus the width over 2, that's over here, all right? That's over there. We want to, if the turtle is trying to go outside the bounds in this frame because it's moving so fast, we'll rein him back inside, make sure that the x is exactly that. And then we want to change the x offset again so that we hit the right wall because we're moving to the right, so we want to move to the left now. To the left now, all right? So this is going to make sure that our we got a negative x offset now, but just that'll take care of it, all right? So yeah, those are the new if statements, and they should pretty much do it. Yeah, does that make sense? How I changed up the ones for the y and turned them into the x? Because the y ones are still correct, and now we know why, right? It's like, all right, if we hit the top or the bottom wall, it's, well, of course, rein the turtle back in, but it's the y offset that changes. We hit the bottom wall, it's the y part of the offset that changes. Don't mess with the x. That was already fine. All right, so that should work, honestly. I think that'll fix everything. And now all of this was packaged in this bounce of hit wall functions. Like, this is the function that notices, like, did we hit a wall? If so, mess with our direction, rein the turtle back inside, have him just graze the wall now, so that he never passes outside. And now draw frame becomes very simple. It's like forever draw frame. And what do I do in a draw frame? Well, move the turtle in the direction, current direction, and then bounce if I hit a wall. See how simple that is to reason about now? It's like, all right, if anything goes wrong with the bouncing, now you just look in this function. Cool. And then turtle x and turtle y has changed in some way, potentially having bounced. Then, all right, just go to that new position that we've calculated for the turtle to be at. Cool. Moment of truth. So the bottom wall is still fine. Left and right. Yeah, look at that. That's beautiful. And it might hit the corner this time. That's nice. Getting there. So that is satisfying, I think. Are there any questions about why this is working? It's like, all right, we've got left and right movement with the x offset. We've got a random one. We've made sure that it's going to be constant speed by doing this normalization process. And now we're bouncing if we hit a wall. Right, every time, and we've got the left and right wall up in there, messing with the x offset if we hit the left wall or the right wall, because we still, if you think about it here, we're about to hit the right wall, so we still want to move up after we hit the right wall. We just want to move to the left instead. So now we're left and up. We negated the x offset, x part of the offset, kept the y the same. All right, so yeah, I think that's what I wanted to say about that. Any questions before I explain some more things? Because there is one last thing I want to talk about here. You may think, I want to talk about this right here. We can't just use a bunch of elifs. You might want to be efficient and be like, all right, if we didn't hit the bottom wall, elif, this one, elif. If that's not true, try this one. If that's not true, try this one. That's more efficient, right? Remember all that. It's like this will only ever do the one that works first. It's like if this is true, do this and be done. Otherwise, try this one. Because elif you read as otherwise, right? Try this one and be done if it works. Otherwise, maybe hit this one, try it, be done. Elif, this one. You can't actually do it this way for bouncing, because what if you did hit that corner? What if you're right there? What does that mean? Now it doesn't mean that you hit just one wall, does it? You did not hit just one wall. You hit two walls at the same exact time, right? And so if you have it as elifs, it will just figure out, like, maybe it was the top and the right wall. If it's an elif, it'll find this one. Okay, top wall, bounce, be done. So it does not configure, it does not handle the right wall hitting as well, because you want this code to run as well at the same time, don't you? You want both of them to happen at once. So elif is just going to try the first one that works and be done with it. So actually, you cannot have elifs here. You need two separate checks for both top wall, handle the top wall, and if we also hit the right wall at the same time, notice that with a separate if. Does that make sense? We need that. You could, though, because you can never hit the top and the bottom walls together, you could make those if elifs, like these can be chained, if you think about that. It's impossible to hit both the top and the bottom wall, that's fine. But the left and the right wall, same for the left and right wall, you can't hit both the left and the right wall. So this can be a chunk, and this can be a chunk, but they cannot all be together, because maybe you hit the top wall, so you want to run this code to handle hitting the top wall, bouncing off, and you hit the right wall. You want to handle it, you want to run this code as well. See that? So, I don't know, it's probably easier to just keep it as a bunch of ifs, because that's kind of how it was at the start. But that's why there are a bunch of ifs. You cannot have just some elifs there. It cannot be if, elif, 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 because you might need to run two of those bodies, and that would not happen if you were to do it that way. All right? Does that make any sense? It's a little bit of a very detailed thing, but it's necessary to talk about that. So yeah, let's try it again. New random direction. This time we chose that one, but it's always going to be constant speed, and we're bouncing off in that way. It's wonderful. All right. So, yeah, if you want to change the speed again, the speed has to do with the length of our direction triangle. So now we've capped it at 1. If you want to change that, you can just multiply it by something. Just be like, all right, I will change this to speed 5. So I'll just multiply it by 5. Now, I forget if this makes it exactly length 5 or like the square root of 5 or something, but it's close enough to 5. All right, so there. It'll be faster now, right? Because I've made the hypotenuse now 5 essentially. Does that make sense? So I change this. Now it'll move faster in its random direction, but it will always move at the same speed. I've capped the speed at, now it's 5 instead of 1. So look at it. That's a little too fast maybe, I don't know. But it's still going to work. See, that was almost the corner. Nice. It's a random direction, random speed, or not random speed. Constant speed. You can change the speed, though, by doing this. Okay. And now we're back to normal. Now it's just 1 again. But yeah, what did we do? Drew our little bounding square, made the turtle the square, picked a random direction for the turtle. That was length 1, and then just kept on going, right? Draw a frame. Change the turtle's x and y by the direction. Bounce if we hit a wall by negating one of our offsets, right? Just 1. Unless we hit a corner, then we do 2. All right? But yeah, that'll do it. And then after all that work has been done, we've just been messing with these variables, right? Turtle x and turtle y. And those have nothing to do with where the box is, right? Those are just variables for us inside the program. Once we've finally put x and y in the right spot, like we've had to rein the turtle back in, do stuff with the direction as well. Like turtle x and y, they're changing. Then actually put the turtle in that spot that we've decided for him to go now. That's a good spot for him. Now we do the go to, right? And just forever until the end of time. Keep drawing a new frame. Keep doing all those things. Lovely. All right? So I think that's what I wanted to say. Any last questions about any of that? So I'll give you this code. It's very good to study, and ask me lots of questions as you're going through it. If you don't have any now. All right. If we're happy, I just want to do one more thing. And then we got to talk about the final too. But I want to talk about moving stuff. I want to talk about using the turtle library to move stuff with your keyboard, because you can hook into the keyboard as well, just like we were doing in Scratch. It's a little bit harder, as usual, in Python. But we can use like key presses to move stuff. Like, make a little character that moves up and down. Because the goal right now is, if you don't see where I'm going yet, I would like to make Pong for us in Python. Right? That would be a nice way to come full circle, because we know how to do that in Scratch. Let's do it in Python too, because we have the ball moving right now, don't we, for Pong? That is most of it. Now we just need a paddle, and the paddle should be movable. Like, there is a way to hook into the mouse, but it's a little bit harder, so we'll just use the keyboard. It's like up arrow moves the paddle up, down arrow moves the paddle down. So let's figure this out, right? So if we want to make Pong, at least in Turtle Land, let's hook into the keyboard. I think that would be the easiest thing to do. So we can also make the turtle the paddle. Watch. The turtle can be the paddle for sure, because you can turn the turtle into a square like we've been doing. You can turn the turtle into a square, and you can stretch the turtle. So right now, what we're doing to make the ball big, or the square big, is we're stretching him by a factor of 2 in the x and the y direction. It's 2, 2. But you don't have to keep it the same. You'd be like 2, 6. That will stretch him more in the x than in the y, or vice versa. So like, this is what I want. If you stretch the turtle more in the y than in the x, you can get him to look like this. Does that make sense? Then it'll be a paddle. That's perfect. All right. So apparently, if you stretch the turtle by 1.5 in the x and 6 in the y, it's a good-looking paddle. I've tried this. So the default size for the turtle is apparently 20 by 20. So if you stretch him by 1.5 in the x, he will become 30. If you stretch him by 6 in the y, he'll become 120 height. And then we'll just make him move up and down with some arrow keys. All right. So yeah, let me walk you through all that now. It'll be a quick example, and then we'll do this more in the next programming lecture. So yeah, it's in the turtle library. If you want to get key presses, it's called on key press. And what you do is you make a function for what you want to have happen when the key gets pressed. Then you say turtle.onKeyPress, the name of the function that you want called every time that key gets pressed, and then a string that represents which keys. Like, capital up represents the up arrow, capital down will represent the down arrow key. And so that's what we'll do. We're going to make a function that we want it to call for us every time a key gets pressed. So we'll make like a function for like move up and a function for move down. And this onKeyPress will call it for us. Okay? So yeah, let me show that to you. It'll just be a quick one. I'll do plenty more of this. Plenty more where this came from next time. So, I don't know. I'll steal most of this code. I'll call it paddle.py. But I want to get rid of a lot of it too. So we got the bounding square. We're going to make the turtle the paddle now. So keep him a purple square, but we're going to like stretch him in a different way. It's like 1.5 by 6. All right. And then like the width is no longer any of that. So if I stretch him by that, 1.5 in the x and 6 in the y, then he'll be like this. That's what I want. Okay. And then we got to give him like a starting spot. So we can use x and y again. So I'll keep those. Let's see, how do I want to do this? Just get rid of all of this. And now the x and y will be like the starting location of the paddle. I'll deal with that later. And then why do they always pick our class to do that, man? Alright, so what do we got? So yeah, I've just like put the turtle in a random spot right now. It'll be probably off the screen, but he's not going to move anymore. But I've stretched him. Alright. So there, that's a nice looking paddle, but it's in a random x and y right now. Let's mess with that. So, I don't know, instead of turtle x, turtle y, let's call it paddle x and paddle y. Because it's going to be a paddle. And then, like we were doing in Pong, I guess, maybe the initial position of the paddle should be like over here on the left for sure, right? So like, let's hard code the x to be over here somewhere. It's like, negative 170 was a good one. And then we can start the paddle like in the middle, so like y equals 0. That would work. So let's just like hard code those things. I think that would work. Yeah, so all I've done is drawn the rectangle, made the turtle the paddle this time by stretching him in a weird way, and now the x and y are these. Oh, and sorry, I need to go to paddle x, paddle y. Not turtle x, turtle y anymore. And so now always he's just going to be over here on the left. I think that's a good spot for the paddle. Now I'll just go up or down only. All right, that's what I want. So the way to do that is with this on key press thing. So you say dot on key press, and you pass along a function that you want called when that key gets pressed, and then a description of which key like you're trying to hook into right now. So we want the up key and the down key. Yeah. So this will be fun. Let's make a function called like go up or something. I don't know. So here. Def go up. So this will be called whenever we want to go up. So how do we move the turtle up? We mess with his y, right? Y gets bigger when we move up. So it's going to be like paddle y equals whatever it was plus like 10 or something. I think that'll work. So yeah, and that's a global variable. So I just have to say global. And so like that's a function that I want to be called for me whenever the up key gets pressed. Does that make sense? And so I can have the turtle hook into that by saying this. Turtle.onKeyPress, like call the go up function whenever the up key gets pressed. That's how you use it. All right, so this sets up the function. Sets up functions to run every time the up/down keys are pressed. Something like that. All right, that should work. Yes, that's what I want. And after you've hooked into the keys, after you're ready, like you've put all your functions, got it ready for yourself, you have to say turtle.listen, because it's not he doesn't know to like begin looking for the key presses yet. You got to tell him like I'm ready now. I've hooked up everything. So you say turtle.listen to listen for the keys, because we have a couple on key presses, right? We want to go up and a go down. Let's make a function called go down that takes the y, and like if we want to move it down, makes the y smaller, right? That's what we want. Paddle y equals paddle y minus 10. And then remember, these are just variables. The turtle is not being moved, really. These are just variables. So like, if you ever change paddle x and paddle y, you should put the turtle to where you've just said, right? Go to those new positions. Yeah, I think that's pretty much it. So go up, do that. Go down, do that. So we want to, on the down arrow, if the down arrow key ever gets pressed, we want the turtle to call go down for us. Does that make sense? That's kind of cool. We're passing the name of a function to another function. That's really powerful. That's something I don't teach my CSCI 40 class even. So this is a very cool concept that you guys are getting to learn about in this class. It makes it easy for us to do things in Python. So yeah, a function can take another function. That shouldn't be weird, I guess. So yeah, we got all the functions. We hooked up all the keys. Tell the turtle to start listening for those keys to be pressed. And then we're pretty much there. Oh. Well, my computer has frozen. Uh-oh. Is it happy now? There it goes. Oh. Global paddle Y. Global paddle Y, sorry. That's the name of the thing I want to be able to change. And now, in theory, if I press the up or down keys, look at it. I'm pressing up, I'm pressing down, and it goes up or down. If you hold it in, it'll move. But right now, we're also allowed to go way outside of the bounds. We don't like that. So, goodbye paddle. So we'd like to make sure that the paddle never leaves the window, yeah? So that will be some constraints on the y, right? So what is the largest y that we want the paddle to have? A similar thing will be true, right? Because this is what? This is y equals 200 again, as usual. So this is like, all right, where is the turtle right now? Because it's always relative to his center. So where in the world is the turtle right now? If he's grazed the top wall, it's not y equals 200 because he's like his height is 120, right? His location's relative to his center. So it's really this line that we care about checking if we're on, right? So that's minus half the height. So there's 60. Go down by that, and so that makes me at y equals 140. So we don't let the y get bigger than 140 now. Okay. That's what we want. So just like rein it, do an if statement, rein the turtle back in if we ever try to go outside of that. So like that's for go up. So like we tried to go up a little bit, maybe that was too much. So make sure we don't go past the top. Like if paddle Y is greater than 140, no, that's as big as it could have been. Go back inside. Just like set it back to 140. See how that'll just keep it always, that's the biggest it could ever be now. If it ever gets bigger, set it back to 140. Never let it be outside of that range. And then the same is going to be true for go down. Boop. So now I can hold it in, I can press as much as I want. It's never going outside because I'm not letting it. Does that make sense? That's what I want there. And then same for go down. It's like you just don't want it to get too small, and you can imagine it has to do with negative 140. Don't ever get any smaller than that. It's like if it ever tries to get smaller than that, set it exactly to negative 140, right? Make sure, and this is make sure we don't go past the bottom. Yeah. So yeah, every time we press those keys, it's going to call all the function for us. The turtle's listening. We'll call those functions for us. We're going to hold it up. Up, 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 up. We don't go past 140. Down, 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 down. We don't go past negative 140. As even though I'm trying really hard and pressing the key right now. Yeah? Yeah, so that's pretty much it. So we stretched the turtle, made him the paddle this time, and we set up these functions to be called up and down, and just like calculate positions, go to those positions, because this line, these are the lines that actually move the turtle, right, on the screen. These are just helping us figure out where to put him eventually, right? Those are just helper variables for us. Yeah, I think that's what I wanted to say. Are there any questions about this example? Because now, to make Pong, we just got to hook them together, right? So yeah, are we good with that? So it'll be very satisfying to get it working. Yeah, so that's all I want to say for this lecture. Any questions about this or the bouncing? I'm going to study the file a lot and get really good at it so that we can make it ourselves one day maybe. All right, so please do attendance if you have not done attendance. I want to stop that eventually. And I need to talk about your final exam. So let's go to that. So we're in week 15. There's week 16, lectures. Week 17, lectures. Week 18 is the final. All right. So here, I'm going to release this final info page. Eventually, the final will be down there, just like there was for the midterm, right? So here's the final info page. The rules are pretty much the same as the midterm. It's just like we get a little bit longer because the final exam is scheduled to be an hour and 50 minutes. So a little bit longer than the class time normally. So it's going to be a bit more time that you'll have to spend taking the test. But I won't make it much longer than the midterm, honestly. So what's going to happen is the final will be from this time to this time. Our time is scheduled for Monday of finals week, so we just get it over with. We come to this room at 11 on Monday, May 19th. So you'll take the test. You'll use the big computers rather than your laptop, right? Just like for the midterm. And so that's when it's going to be and where it's going to be. And yeah, here are the topics that I will choose from. Here's what I will ask you to do. I'll ask you to write an essay, similar length to the midterm. And then I'll also ask you to write Python code. All right. I'll ask you to write programs. All right. So study everything I've asked you to do, all your programming assignments, all the stuff that I've been doing in class, because that's where I'll take things from. Let's see here. So yeah, just prepare, study the programming assignments, study the in-class examples. Like for sure, I'm going to ask you to do turtle stuff, for example. All right. So yeah, the essay will be kind of half the grade, more or less. And yeah, the rules are going to be the same, mostly the same as the last midterm, but I'll let you use idle. So here, you're going to take the test on Canvas as usual. Be closed book, no notes, except for you get one cheat sheet, just like you had on the midterm. And so you can put whatever you want on it as long as it's handwritten, right? It has to be handwritten, can't print it out. You can write on both sides. You can use idle to program and test your program during the midterm, or sorry, during the final. All right, so come and install it because you're going to have to use the big computers. Make sure it's installed before you start the test, right? So you can test out your programs that you're eventually going to put into Canvas on idle, but you can't like go on the Python website or anything. Does that make sense? You can use idle to test things though. You can run your programs, make sure they work before you finally submit the answers. And then, of course, you get as much scratch paper as you like. Nothing else, all right? You got to be on Canvas the whole time. Can't go to any other page on the internet. Can't use a calculator. Nothing other than those things. But at least you get to look at your programs and make sure they work before you submit. All right? So I think that's about as fair as I can make it. Are there any questions about that? Does that make enough sense? So yeah, just make sure, I'll try to get here a little bit early. There might be a class in before us, though. I'm not sure, like, how the scheduling will work. But, like, you'll have some time. Like, it won't take the full time. I'll do my best to make sure that it doesn't, so that you'll have, like, 5 minutes at the start to install idle if it's not already installed on the computer you're going to work on. Okay? So yeah, that's when it's going to be, what it's going to be on, and everything that's happening. I think that's all that I wanted to say. Are there any last questions about any of that? We know when it's going to be, what's going to happen. All right, so yeah, let me know if you have any questions about anything as you think of them, but I think that is officially all that I have for the day. Make sure to do attendance. I will stop that in a minute.